chapter, this one. Alright, so chapter 3 is about 60 slides, so it's going to take a while, so we'll get started and look at the protocols and the models that we use to talk about how traffic is generated and handled within the host machines, or any machine on a network actually, so that we can understand how various elements work in getting traffic from point A to point B. So we'll look at the roles and types of functions within each device on the network, the main protocols that we use. These protocols are governed by standard organizations, and we'll be looking at both the TCP IP model and the OSI model while doing this course. It's very important that we have something to break down the features and the functionality of the protocols and how they interact with each device. So we'll look at how data is encapsulated and transported across the network and how it's accessed. So rules. Every type of communication we have as humans have rules attached to it, be it grammatical or whatever. So computer communications are no different. We have a set of rules. These are how to handle stuff from a sender, a receiver, and the media that is used to cover it. Now, when we're talking about humans, we have person A and person B, and the media is going to be air, and the message is transported via our voice using a specific language. So devices use exactly the same principles to communicate between each other. They need a source and destination and a language to talk to each other. So we have rules that govern how the conversation is established, how it proceeds, and how it is finished. We normally greet each other. Good morning, how are you? Good, back and forth. We have manners and that govern how we talk to each other. So the protocols need to identify the individuals involved, who's sending and who's the receiver, what languages and syntax they're going to use, the grammar, how fast the to and fro, the speed and timing of the delivery should be, and what types of acknowledgements are going to be used. I mean, when we're talking, we often nod at various points during the conversation to acknowledge, yes, we've received that point, or I agree with you, that sort of thing. So network protocols have to do all of this within the confines of digital media. So we need to bundle the message up for transport, which is called encoding, and we need to have a format for that to be delivered in. which we need to sort of break it up into usable size chunks, how long, what's the timing between chunks, that sort of thing, and what types of options for delivery do we have. Now, we have lots of variables in this information that we need to send back and forth. So encoding is basically putting it into a form for transmission, and decoding is reversing that encoding. So most of the time we're going to say the language is the encoding, yeah? So when you say language and encoding, we have to define which language it's going to be used, and that's basically what we're doing. So the formatting and encapsulation is we put it inside an envelope. All right, so taking it back to the old snail mail days, here's our message on the letter. Dear Jane, thanks John. We put it in an envelope, so that's encapsulation. All right, we're wrapping it up. Now, the format, that kind of depends on what the message is being used for. But the format for snail mail is you tend to have the name and the address of where it's going, and then the returning name and address, and postage paid, so authorization to be sent. So when we're doing that via a protocol, we have a source and destination addressing, okay, and we have some other headers here which we'll go into in greater detail when we actually do the TCP IP chapter. But you should be aware that there's IPv version 4 and version 6, so we need to specify which version of IP we're going to use and how much of there is, and I'll explain that later. So basically confirming what the language version is and giving it a destination address and a return address. Sizes need to be specified. Now, generally speaking, we're going to send stuff in 1500 bytes or less, and all of this has to do with how we send our little bits of information across the wires, or the flashes of light or sound or whatever it is that we're using to transmit the message, so that the other end can receive it and interpret it and then look at the next chunk of information. So we need to have spacing between words, sentences, taking a breath, that sort of thing. And that's okay, Chris. Welcome to the chapter. So message timing. So the things that address message timing includes flow control, which defines and controls the rate. Response timeout is we've agreed how often we're going to acknowledge receipt of our packets. So how long do we wait before we go, oh, we haven't received an acknowledgement from you? And access method is how we can access the media for sending it. So what do we do if two individuals talk at the same time over the top of each other? When we're doing it via electronics, both messages get garbled when people talk over each other. Just like most cases in a human conversation, it's hard to pick out the conversation that you want to listen to when somebody's talking over the top of you. So we've got to have all these rules governing who can talk, when they can talk, and sharing the same resources, well, between multiple people. So delivery options. Okay, most conversations are between one device and another, so this is called Unicast. One-to-one communications, as it says there. One-to-many, so if you're talking to a selection of people within a group, that's called a multicast. Okay, so you're talking to some individuals, but not all individuals within a group. And a broadcast is where you will send the message to everybody within the group. Now, these definitions are a little different in IPv6, and we'll define those better when we do the IPv6 specific chapter. Now, so because broadcasts aren't really there, we've got Unicast there. It's wait until we get to there. Now, some of the documentation you'll see about the types of communication delivery options may use node icons, which are just dots. So we're just, in this slide, just making a point that showing it this way or this way, okay, so instead of a single yellow saying, oh, this is the source and this is the receiver, this is the destination. In node iconology, if you like, it's just, here's our source, here's our destinations. These other colors aren't recipients of the message. So protocols are definitions of rules on how to communicate. They can be implemented in hardware and software. Like how that doesn't roll off the tongue very well. So basically we can define it in software as in applications, operating systems, or it can be hard-coded into physical hardware itself if needed, or a combination thereof. So protocols have their own function, their formats and rules, and they are governed by the standards that they comply to, which, well, there's a slide on that coming. So network protocols have to have an agreement between the devices on how they're going to communicate. And what features they're going to use during that conversation is basically, well, the protocols negotiate between the two devices. So functions that are defined under protocols are the addressing schemes, reliability, how it's going to guarantee that information gets to the other end, how that information is going to flow efficiently between the points, sequencing, so that if different paths are used, your timing might get out of sequence. So you need to be able to reorganize the information when it gets to the other end into the correct order. Whether any errors in transmission or transport have occurred, so error detection, and the application interface, how the actual application is going to use the protocol in question. So we've got lots of different protocols and each have its own function and format. So when we're talking HTTP web pages, it's totally different to what Ethernet defines, for example. So HTTP defines how we use hypertext markup language to display a web page from any source to a browser. But Ethernet controls how we're going to access the physical medium and transport that message. So there's various different protocols to get our information from our source to our destination. So we've got the protocol that is the application being discussed and using the service. We have the transmission control protocol that controls the flow of the conversation. We have the internet protocol, which is the actual delivery protocol, and then the Ethernet, which governs the actual access to the media itself. So rather than having individual discrete protocols all separately references, we bundle some of these together into a protocol suite of interrelated protocols that need to be used together for our conversations to occur. In terms of how we look at protocols, we can break them up into upper layer and lower layer protocols. So upper layer protocols, we talk about how the applications and that control the conversation. So what the format's used, what the timing is, how it's going to flow across to the other device. And then the lower layer communications is actually about getting it from point A to point B. So one's sort of holistic and one's practical. So the main ones out there are TCP IP, which is the Internet Protocol Suite. And that is the one we will spend most of our time exploring. You have OSI, Open Systems Interconnect Protocols. There is still one protocol that is used out there that this organization still uses quite a bit in industry, and that's called ISIS. Okay, Apple Talk, proprietary to Apple Inc. Has its own issues. Well, it used to have whenever I used to deal with Apple servers, which is quite a number of years ago now. It had major issues. The Apple server used to keep falling over on a regular basis, like at least once a day. Novell is, well, it was the best networking operating system out there. Unfortunately, with the advent of Windows being adopted throughout the land, and a lot of the functions that used to be handled from Novell incorporated into Microsoft's operating systems, Novell's networking operating system disappeared. which is sad because it used to be a very powerful and secure operating system for networks. That's a conversation for another day when we're back in classes, which I'll talk about after the recording again. TCP IP protocols examples. Basically we'll be doing a lot of these. So basically it uses a system of protocols that govern how the application talks to the transport layer, and the transport layer governs how it accesses the internet, and that in turn governs how we access the network. Now, we'll get into it, but basically when we're talking about any of these models, you can always assume that whatever layer we're talking at or looking at, so in the example here, application, it will talk, the application layer will talk to the application layer from the source and destination, as well as the transport layer directly above and below in the protocol stack. Okay, so the internet layer at the source talk to the transport layer and the network access layer. So one up, one down. And it'll talk to its counterpart at the other end. What protocols make up the suite? So within the Internet Protocol, the TCP/IP suite, in the application layer, we have our most common ones that people are aware of. Domain name server, dynamic host configuration protocol, our email POP, simple mail transfer protocol, IMAP, which I can't remember what it breaks out to, file transfer protocol, simple file transport, trivial file transport protocol, hypertext transport protocol, secure, REST. I'm not sure what that one is. Don't know, can't remember off the top of the head, so sorry. Then in the transport layer we have TCP and UDP, which is basically one is reliable and one is not reliable, and we'll look at what makes it connection and connectionless, and that we'll explore these two in detail later on. Internet layer, we have the IP addressing schemes, the network addressing translation that is used to increase the availability of addressing, routing protocols and routed protocols. Let's get this one cleared up straight away. The routing protocols talk between the routers to share routing information on available networks throughout the network. Our routed protocols are the protocols that are talking between the end devices. So the routers use the routing protocols to keep themselves up to date and manage themselves. And the internet protocols in this example are the routed protocols that are used to get you from point A to point B across those networks. Various messages to manage the network. So we'll look at those in details. So our testing, ping, trace routes, are all part of ICMP messaging suites. Network access layer, so address resolution protocol, Ethernet, and wireless LAN protocols. So basically, address resolution is we have two layers of addressing. We have a logical layer and a physical layer, and the address resolution is to map or join one to the other so that communications can occur. How does it work? Well, when we request information, it is broken up into data segments, and the TCP adds information to it for how it is to flow. So this is where our sequencing and reordering and all of that occurs. IP is where our addressing goes in. Our Ethernet is where our framing information goes in, and then it finally gets put onto the wire or the medium is ones and zeros, which we'll look at in more and more detail throughout the other chapters. Okay, I'm not going to read out all of these. I'm just going to say standard organizations are there to control the protocols and other areas so that we have the ability to work together across any vendor-specific equipment. So that's what interoperability, competition, and innovation covers, is basically, yes, you've got the various manufacturers out there, but they need to work together for networking to be effective. So they control how they're going to talk to each other. They're not for profit, and they're there to make all the manufacturers work together to the betterment of the internet. So under the Internet Society, we have the architecture board, and then the research task force and engineering task force, which have various groups within them that are doing improvements to the way things communicate over the internet and networking in total. So INA is our Internet Assigned Number Authority. They're the ones that oversees and manages the overall pool of addressing, domain names, and port numbers. So application identifications, which are what port numbers are used for. And the Internet Corporation of ICANN is, a side thing. It used to be the body, but INA is now the main body. They've broken the functionalities up a bit. I'm going to let you read through all these various standards and IEEE, EIA, GIA, blah, blah. Yes, even I find it exciting. Okay, reference models. These two models, OSI on the left, TCP on the right, are the two models that we will be using to show the various functionalities of and elements of the protocol suite and how they work going forward. So OSI model was the first one that was adopted. This is our Betamax. And TCP/IP is our VHS. And you're all looking at me going, what the hell are you talking about? Well, us old fogies remember the old days when videos came to the home market, the movies on videotape. There was two main brands. There was Betamax, which was technically the better, and then the VHS, which is the one that had the more movies available on that format. So this is the one that everybody adopted, and this is the one that was technically better. So, all right, so the OSI model has basically been relegated to a teaching function, but it actually described how each element of a protocol and communication should interface with each other. And by having it via a model system like this, you could break up the tasks into various working groups, and they just had to agree on the interface points on how they're going to talk to each other, and they could just individually work in their own elements. And that's how protocols work. They work within their own little bit, doing their own part, and then interface with the layer or the functionalities above and below it, and its corresponding bit over there. So under TCP/IP, we have application, transport, internet, and network access. And as you can see by this graphic, they don't map one-to-one because you have 7 layers in the OSI and only 4 in TCP/IP. So your task is to remember both models and how they map to each other. Isn't that fun? There's lots of different little limericks and that sort of stuff that float around for you people use to help remember these. When I first started, it was, please do not throw server parts away. Okay. That one I have no idea about, but that was the OSI one that I used to help me remember the order. So by using layered models, we can do coordination, ABROC, between the various layers. It helps foster innovation and competition between vendors because they are just working to the same goals because they're working within the model, and hopefully we get a better product at the end of it. Okay, so under the OSI model, starting down the bottom, physical layer describes how we access our physical connections. So how do we activate them, maintain them, and then shut them down when the conversation ends? Data link is our interface between our software and our hardware. So this is the method of exchanging information between the actual operating systems and the physical hardware. Network provides our interface for addressing. So we've got 2 addressing elements. So we've got addressing that works here in the data link, which is known as physical addressing, and then addressing that works on the network layer, which is known as logical addressing. Just file that away for future reference. Transportation controls how we're going to segment that data up, how to transfer it and reassemble it at the other end. And then the upper layers here provide how the application's going to access the network. The presentation is an agreement on the formatting of the information, how it's going to look, what type of imaging, all that sort of stuff is here in the presentation and sessioning. So the session basically opens up the conversation, which is a little different from our TCP IP model. Our network access controls the hardware devices to access the media. Our internet determines our path through the network. Our transport layer is the one that controls the communications between the devices, and then the application is where our host device requests services of the network. So again, these two models, you must know, they are going to be your friends to work out how things work in the coming chapters. You're going to get so sick of referring to these things, and we do lots of referring to these models, and you need to know them. Have I said that enough? Hope so. Okay, de-encapsulation. So we already stated that we need to break our messages up into chunks. This allows us to what's called multiplexing across the network by putting the messages into smaller pieces. We can interleave them with other messages using the same resources. So part A of message A can be put into or in between segments of another message that's already in the process of traveling across the network. This increases the overall speed of the network because we basically don't have to wait for large chunks of data to be successfully sent across the network before other conversations can access it. And it makes it more efficient in that if something goes wrong with part of the conversation, we only need to fix that little bit of the conversation, not the entire conversation. So it's more efficient. So the sequencing is basically tags that tell us what order the message is being broken up into so that it can be reassembled at the other end in the correct order to make the message make sense. Now, we use protocol data units, PDUs, to describe what stage of handling, if you like, is occurring. So we start off with the data being sent, and the first thing that needs to happen is it be broken up in those smaller data segments so that it can start its traveling. We add transport header information into that data, and this is now called a segment, a piece of the data. We then pass that down to the IP or internet layer. So that's the transport layer, that's the application layer. We give it the network source and destination addresses. Okay, so we're wrapping it up into another bundle, and this bundle is called a packet. And then when we pass it down into the data link layer, we add framing information front and back, which basically says I'm a start of a frame, I'm the end of the frame, so that the devices know this is a start and this is the end. I can stop listening and compiling the ones and zeros. So that frame is then put into the actual media as bits, the ones and zeros. So encapsulation down, pretty much as per the other one. So our data is encapsulated with each layer's information. So think of it as the old Russian dolls. Okay, you have one doll inside of another, inside of another, inside of another. Okay, and when it gets to the other end, it removes the outer casing back down to the original data. So addressing, we need source and destination addressing both in a logical and physical method. So taking it back to the old snail mail, your logical address is the name of the individual. Okay, your physical address, your physical address is the actual house address. So you will tend to have multiple people living in the same house. So how does that translate to networking? Well, you've got a physical device, so that needs a physical address, but it can be given a random address on the network. Okay, so when we look at logical addresses, it's looking at the identifying the recipient of that. And when we talk about it in terms of networks, and I need to use our pointer options, change the pen. Okay. So when we're talking about a network, we have a router and we have a whole stream of network cable. Okay. And we have our individual devices hanging off the network. Okay, so we have a physical address for each device on that network. Okay, but those physical addresses are only unique to this segment of cable. So we use the logical address to get it from other parts of the world out here into this part of the network that, okay, so that's the logical addressing. It gets us to our destination. But along the way, the physical addresses only refer to the devices on that shared media at that time. So we need to match these two addressing schemes together. Okay, so we get to our destination, our final piece of cable, and it's addressed to M3. So M3 knows to listen to the frames and pick them up using the data link source and destination address. It then confirms with the layer 3 or the network layer address that it is a valid recipient at this physical address. That gobbledygook will become clearer as we work our way through the addressing schemes moving forward. Trust me, I've been doing this a long time. I know it's a lot to take in right now. We break this chapter into much smaller individual pieces of information and go into it in more detail as we go through this first unit. Okay, so source and destination IP addresses are telling you the ultimate final destination for the IP packet to travel. Okay, so we are basically going from our PC here up to our web server, and it's going to be looking at the destination to get there. It's not going to be looking at the source. It only wants to know the destination network. Okay, so comes up here, looks in routers 1 tables. Do I have an entry for the 172.16.1 network? Yes, I do. I need to forward you to router 2 to get you there. Router 2 looks at the network and goes, yes, I know that network. It's this piece of cable. I'll put you on there. And then it will get to the individual web server, which is the host 99 on that piece of cable. And then when it wants to reply, it flips that source information. That becomes the destination, and that becomes the source on the return trip. So based on that, I was leading to this in that within each addressing space we have two parts. We have a network part and a host part. Now, these are defined using our subnet mask, and in the original days, this number determined which was which. So 192, we would say the first 3 octets were network, and the last one was host. That was just the old convention. 172, we would say the first 2 are network, last 2 are host. So we'll look at that when we look at the individual elements of addressing, when we look at the addressing. So at this point, the network portion is used to do the routing, the forwarding information from the router's perspective, because routers join networks. They don't join individual hosts. So they will just look at the host portion to make a forwarding decision, and then the host portion comes into play on that final segment of cable where the host resides. Okay, just the physical addresses and network addresses work together to get it to the destination. So in this example, we have the frame header. All right, so our A and our C. Now, because our logical address says it's part of the 192.168 network .1, so they both, the source and destination, are on the same portion of cable, so we're not traveling through the router, we're staying in here. We use the MAC address to tell us that we are traveling from here to here. Okay, so this is where this framing convention addressing comes into play. It tells the FTP server to pick up the frame because it is CCC. It'll then pass up the packet to the network layer. It will check the IP addresses and say, yes, I am 192.168.1.9, and I will action the data. Now, the role of that MAC address is embedded in the network interface cards, and it's only called a MAC address while we're talking about Ethernet. When we get into different protocols that work on layer 2, they still use a physical addressing scheme, but it's referenced as other names because it's a different protocol. So when you hear a MAC address, it is the physical address component within the Ethernet protocol. And it's used to create an individual address of a physical device on the same segment of network. Now, we say segment or of network because in the original days, we used to have a piece of cable, coax cable to be precise, and we would tee off that cable and put a host on it. So each host shared a segment of cable, and the MAC addresses identified each host that shared that individual piece of cable. The cable was the network. Back in the dim, dark ages. Okay. So if our destination is not on the same piece of cable, as in network, the address used at layer 2 identifies the gateway. How do we get the IP packet off this segment of cable and moving towards its ultimate destination? So the source stays the same, but the destination is the device that needs to process the packet along its travels. So the gateway would be addressed. So this tells the frame should travel to the router, the gateway, and then the gateway will look at the IP address and say, I need to forward you on to the next device, and this would now be the source MAC address, that would be the destination MAC address. The IP header doesn't change. These change each hop. That becomes the source, that becomes the destination, that's the source, destination, source, destination. Only at layer 2. So the layer 2 information is a per hop, and layer 3 is final, the overall. Okay, so basically, to recap, layer 2 addressing identifies the physical device to pick up the frame to action the contents. The logical addressing tells the device whether or not it is the final destination in the journey. Alright, so you go through the gateway, it forwards it on to the ultimate piece of cable where the host actually resides. And the data link layer changes along that multi-segment path to tell it each individual device needs to pick it up, action it, and then forward it on to the next hop. And this is just going through all that explanations that I did on that slides earlier. So I'll let you read it at your leisure. I'm not going to go through it again, because I like sending people to sleep. I know that, but there is a limit. Okay, so one of the first labs that it'll ask you to do in this chapter is download and install Wireshark. You can find it at wireshark.org, and it's a fairly simple thing. If it is quite a powerful tool in our arsenal to do traffic analysis. Okay, so it is worth us exploring and looking at, and Wireshark themselves has a page with tutorial videos and information on it, on how the application actually is to be used in depth. We will provide you with a very basic overview as part of the course, but if you wish to explore the capabilities of Wireshark itself, there's multiple videos and command structures and all this sort of lovely information on their website. Well, it's basically done, mate. So you're not going to miss anything. But yeah, close it off. So in conclusion, we talked about the protocols being the set of rules to communicate between a sender and a receiver. And these rules include how the message is to be formatted and packaged up for transmission between the source and destination. We looked at various protocols and how they work together in a suite to provide that functionality. And we looked at the fact that there is a series of organizations that control how the protocols work. We looked at the TCP IP suite, the TCP IP model, and the OSI model. And we looked at the differences between the 4 layers of TCP and the 7 layers of OSI. And we discussed how each step through the models has a different descriptor called a protocol data unit to indicate where it is during the process. So we have the data, the segment, the packet, the frame, and the bits. That by using the appropriate PDU, we communicate where in the process we're talking about. We had an introduction in layer 2 and layer 3 addressing and how they are used together to uniquely identify the destination and source of the communication. So layer 2 MAC addressing only has local network significance. Layer 3 has global significance. It will take you through to even a remote location and is fixed for the source and destination as we travel. So our layer 3 doesn't change, but our layer 2 addressing does as it goes through the network. And that brings us to the end of chapter 3. Okay, good and bad points. Good points is you're still awake. I'm hoping you're still awake. Bad points, you now are faced with a combined exam that is chapters 1 to 3. Okay, the Introduction to Networks uses a combination exam test. So you do less actual exams, but they're bigger because they cover multiple chapters. Whereas our IT Essentials course, you get a chapter test at the end of each chapter. So I'll be turning that on and doing that. Now, let's drag this one in. So, yes, I know it's enabled. Thank you very much. So, Wireshark.org, just go to downloads, select your appropriate installer and run it. And then we'll look at in next week's. I'll do a separate video on Wireshark. I won't do it today. I know we've gone through a lot of information today on this one and yesterday with the virtual machines and that, so there's been a lot of information to take in this week. So I'll do a separate little section on Wireshark, alright, and put it up as a video separately so you don't get totally overloaded right now. Various labs as we move forward will get you to do packet inspection using Wireshark. Now, Wireshark we can use between VMs, for example, to see what traffic is coming and going between the virtual machines. It's not so easy to stick a Wireshark in and listen to the packet flow via packet tracer. Okay, so that's going to be problematic there. But when we get back into the classroom and back on physical equipment, we will be able to do proper examples on how Wireshark works and take it from there. It is worth actually watching and doing. Going to finish the recording there.